next reaction we are going to consider for alkyne is hydration. Okay, so remember we have done hydrogenation of alkyne, we have done halogenation of alkyne, we have done hydrohalogenation of alkyne. So the fourth reaction I'll talk about now is hydration. Okay, hydration. Okay, so this hydration simply means addition of water. Is that not so? Addition of water. That's what it means. So this addition of water to an alkyne will follow the Markovnikov's rule. So the catalyst for this reaction is H2SO4 and mercury sulfate. These two. Okay. So let's quickly look at an addition reaction. So this reaction is different from is a kind of a little bit complex because it forms an intermediate, and that intermediate will have to tautomerize. We'll call it tautomerize. Tautomerize. I will spell it for you when I want to explain it. It's a form of is a kind of a rearrangement reaction. Okay, because what this reaction forms as an intermediate is an unstable compound called an enol. So that enol will have to rearrange itself in a process called tautomerization. The enol will rearrange itself in a process known as tautomerization. So this tautomerization, I will explain it when I get to that point. But so the final product of tautomerization is not the final answer to this question. So let's carry out this reaction. So for example, let's say we have a ethyne reacting with water, okay, in the presence of the catalyst, which can be a mixture of this, or you can use one of it. Okay, so in this reaction, what happens is that the catalyst here, or everything here, will propel this water to be added to this guy following the Markovnikov's fashion or Markovnikov pattern. Okay, so according to the Markovnikov's, hydrogen will definitely go to this side, and the OH, remember water has H and OH, so H will go to this side, OH will come to this side. So and you still have the double bond here because you just added just two of them. So I'll have CH3, C double bond, CH. Then remember you added OH, and you added H here. Okay, so this is what we call enol. Enol is a carbon to carbon double bond that has an OH group. Enol is a compound that has a carbon to carbon double bond, and at the same carbon to carbon double bond, an OH group is attached to it. So this enol is unstable, and it is the intermediate. It's an intermediate. It's not the final answer. Okay, so this enol, I'll complete the reaction here. This enol you are seeing here will rearrange itself, will undergo a form of a rearrangement, and that rearrangement is what we call tautomerization. Now, tautomerization is simply the rearrangement of the proton. Look at this proton. This proton you are seeing here, remember, this thing is bonded like this. It is bonded like this, okay? Or let me leave it like that. This hydrogen here will migrate to this place, to the next carbon, to the adjacent carbon. This hydrogen here will migrate to the adjacent carbon here, and then this pi bond will rise and join this oxygen that is here. Remember, if the hydrogen leaves from here, if the hydrogen leaves from this oxygen will become negatively charged. So to stabilize the charge, or to stabilize it, the pi bond will now join it to stabilize it to become neutral. So what? No, if it leaves, yeah. So when it leaves, the pi bond will now stabilize this. So what I will have here now becomes CH3, C double bond O, because this bond now has risen up. Hydrogen will come here. I will now have single bond CH3. So at the end of this hydrogenation, at the end of this hydration reaction, the answer to this question is acetone. Acetone, or you can call it propanone. Acetone, or this compound here is called acetone or propanone. Let me do one more example to clarify you on this. One more example. Let's carry out this same reaction using but3-ine. Look at this one. Let's use this one as a case study. First of all, carry out your, okay, for this one here. For this one, there is no need to apply Markovnikov's rule because anyhow you add it, it will still give you the same thing. So I will definitely have water. I have H2SO4. I'll have HgSO4. So if you carry out this hydrogenation, this hydration reaction, and you can add hydrogen or OH to anywhere because the alkyne will still give you the same thing anyhow you add it. So I'll have CH3, C, let's add OH. Okay, I don't think this will enter here. Let's redo it. So let's say we have CH3, C triple bond, C, CH3. Okay, then we have addition of water and then the catalyst H2SO4 and mercury sulfate. Now, if you add water, I told you this one there is no need to apply Markovnikov's rule because anyhow you add it, you still get the same answer. Okay, so you have CH3, C, let's add OH here, for example, double bond, C, let's add H here, and then we have CH3. So now, what next? This is the enol, that's the enol. So the enol will rearrange. How will it rearrange? The hydrogen from here will go to the adjacent carbon, which is this carbon, the one that has double bond. Then the pi bond will rise. Okay? When that happens, we have CH3, C, double bond O, CH2, CH3, something like this. Okay? So this is the answer to this question. So this compound is called butanone. Butanone is a ketone. It's a ketone. Okay, some people call it 2-butanone, some people call it 2-butanone, but it can also be called butanone because we don't have anything like butan 1 ohm or butan 3 ohm. So just 2-butanone is the same thing as butanone. So this is just a simple reaction involving hydration or addition of water to an alkene. So what has happened here is what we call tautomerization. Remember, it's the rearrangement of the enol. The rearrangement of the enol to give us a more stable compound. So this is stable. This is more stable. This is unstable. This enol is unstable, right? This enol is unstable. Take note of that. So this is simply what we mean by addition of what? Water to an alkyne following the anti-Markovnikov's rule. Now, let's look at, before we look at the next reaction, let's also look at the acidity of alkyne. Because the next reaction is important that we understand acidity of alkyne. Remember that alkynes can be, we have terminal alkynes and we have non-terminal alkynes. For terminal alkynes, they have this kind of formula. For non-terminal alkynes, they have this kind of formula. Now, any alkyne that the triple bond is in on the first carbon, number 1 carbon, is a terminal alkyne. And terminal alkynes have what we call acidic hydrogen. The hydrogen you always see here is acidic. Okay? Non-terminal alkynes do not have acidic hydrogen because they are triple bond, or you can call them internal alkynes. You can call them internal alkynes. Internal alkynes. Internal alkynes can also be pronounced as non-terminal. So this and this is the same thing. Okay? So for these alkynes, this one is acidic, more acidic, even though they are weak acids, but they are acidic. Okay? Why? Because this hydrogen here can be donated out. Remember that according to Arrhenius, those acids that can donate a proton or that can liberate a proton during reactions are called Arrhenius acids. So this acid, this alkyne here can liberate this proton, and when it liberates this proton, it forms something like this. A carbon with a negative charge plus the hydrogen that is removed. So this thing we are seeing here is what we call acetylide. We call it acetylide ion. It's called acetylide ion. This acetylide ion can react with elements, with compounds containing sodium, silver, to form a precipitate. So this acetylide ion has a way of reacting with compounds or to toluenes, even to toluenes reagent. You know, toluenes reagent is silver nitrate. It will react with it, and this silver will be what? Precipitated at this point here. So these acetylide ions are also very important if you want to elongate the alkane, so the alkyne. If you want to elongate the alkyne, find a possible way to remove the metal or whatever that is here, and then the alkyl group subject this reaction to, let's say for example, subject it to reaction with alkyl halide, RX. Then the metal that is here will pick up the halogen in the alkyl halide, and then the R will come here and then elongate the alkyl. So if you want to elongate an alkyne, you can use a terminal alkyne to do that. Okay, a terminal alkyne can subject to several reactions that can lead to the elongation of the alkyne. Let me show you for example. Look at this reaction. If I have let's say I have CH3, C triple bond CH, and we are reacting this alkyne first with sodium amine and second with ethyl bromide. For this first reaction, what we're going to get, sodium amine reacting with the terminal alkyne will form acetylide. Okay, so we're going to have CH3, C triple bond C. The sodium will replace the hydrogen here. We have Na plus ammonia. How did I get the ammonia? NH2 plus 1 hydrogen have given ammonia. Then subject this one now that is formed here with this guy CH3, CH2, Br. The Br will pick up the sodium, okay? Then the ethyl group here will attach here. So I'll have CH3, C triple bond C, CH2, CH3 plus bromine and sodium will form what? Sodium bromide. Now, looking at this reaction, you will see that the alkyne has been elongated. So to convert a terminal alkyne to non-terminal alkyne, we carry out these two reactions. It mustn't be this one. They can use silver nitrate. You can still use, so far as there is a metal that can cleave to this point to form the acetylide, which will further react with the alkyl halide. This group of compound here is called RX, alkyl halide, to form the elongated alkane. So take note, terminal alkynes can be elongated by reacting with what? Something that will precipitate the metal, and then also something that will elongate it, such as reacting with what? With an alkyl halide. So, in terms of acidity, terminal alkynes are more acidic to non-terminal, and it's only terminal alkynes that can precipitate these metals. Non-terminal alkynes or internal alkynes cannot do this that this guy is doing. So that is what I wanted you to understand in terms of what? Acidity of alkynes. Also, let's compare alkynes, alkanes, and alkane. Which is more acidic? Alkynes are more acidic than alkanes. Alkanes are more acidic than alkanes, that is single bonds. Remember, as the percentage S character increases, their acidity also increases. The percentage S character in alkanes are 25%. For alkane is 33.3%. For alkyne is 50%. Okay, I know you know how to solve this back in hybridization. Okay, percentage S in sp3 is 1/4 times 100/1. This is give you 25%, right? And also percentage S in sp2 is 1/3 times 100/1, which is 33.3%. while percentage S in Sp is 1/2 times 100/1, which is 50%. So notice the increase in these characters as you move from alkane. So this first one is peculiar to alkanes. Take note. Okay, this one is peculiar to alkanes. This one is peculiar to alkynes, right? So as the percentage S character increases from alkane to alkyne, their acidity also increases. So alkynes are more acidic than alkanes. Alkanes are more acidic than what? Alkane. So in terms of acidity, alkynes are more acidic. But when we now look into alkynes, especially the terminal alkynes are more acidic than the non-terminal or the internal, because the terminal alkynes have an acidic hydrogen. They have an acidic hydrogen which they can donate during reactions to form acetylides, to form what we call acetylides. And these acetylides can further react with something containing a metal to form a stable compound here, because something needs to neutralize this charge. So what can neutralize this negative charge is a metal, because metals are positively charged. So they will come and neutralize this charge. And when this is formed, it can still further react to elongate this alkyne. So elongation of alkyne, terminal alkyne, is possible by reacting with something that will give us a metal here, and then treat that compound with an alkyl halide, because definitely the halogen will be picked up by this metal here to form sodium bromide or sodium halide. Then the alkyl group will now join this place to elongate the alkane and make it longer. So notice here I have only 1, 2, 3. But at the end of this reaction, we'll now have 1, 2, 3, 4, 5 carbon at the end of this reaction. So this is what I mean by what? Acidity, terminal acidity of alkynes, and how we can use it to elongate the carbon or to form the acetylide ion. But non-terminal alkynes cannot do this.